Hello friends, welcome to my lecture on convolution theorem for Z transforms. We will begin with the convolution theorem, which says that if we know the Z transforms of two sequences, say un and bn, Z inverse uz is equal to un and Z inverse bz equal to bn. Then the theorem says that Z inverse of uz into vz is equal to the convolution of un and bn, and the convolution of un and bn is denoted by un star bn, and this is defined as sigma m equal to 0 to n um bn minus m. A similar theorem on convolution is there in the Laplace transform, where we say that if we know the Laplace transforms of two functions, then Laplace transform of their convolution is equal to the product of their Laplace transform. So, here also if we have two sequences un and bn, then Laplace Z transform of their convolution is equal to product of their Z transforms. So, to prove this, let us see by definition of the Z transform. Since uz is the Z transform of un, Z transform of un sequence is equal to uz, we are given, and Z transform of the sequence bn we are given as vz. So, we can see that this is equal to sigma n equal to 0 to infinity un z minus z to the power minus n, and this is sigma n equal to 0 to infinity vn z to the power minus n. So, when you multiply uz and bz, what we will have then? uz into bz will be equal to sigma n equal to 0 to infinity un z to the power minus n, this is uz, and bz over in bz we will take the summation over some other index, let us say m equal to 0 to infinity bn z to the power minus n. So, this is uz into bz, and then okay, we can write it in the expanded form. So, this is u naught plus u1 by z plus u2 by z square and so on, and here it is b naught plus b1 by z plus b2 by z square and so on. Now, when you multiply, these two are infinite series. So, when you multiply, we can collect the coefficient of z to the power minus n. So, collecting the coefficient of z to the power minus n, what we will have is the coefficient of in this product the coefficient of z to the power minus n will be u naught bn plus u1 bn minus 1, u2 bn minus 2 and so on un b naught. This can be written as sigma m equal to 0 to n um bn minus m. So, this is the coefficient of z to the power minus n when you multiply these two infinite series, and with this we can write it as, so therefore uz into bz, uz into capital Bz may be written as summation n equal to 0 to infinity, and then this expression sigma m equal to 0 to n um bn minus m into z to the power minus n. So, the coefficient of z to the power minus n is this sum, which is given by the summation notation sigma m equal to 0 to n bn minus m, and by our definition this sum actually denotes the convolution of the sequences un and bn. So, this is Z transform of un and bn. So, this from here we can say that Z inverse of uz into bz is equal to un star bn, and which is equal to summation m equal to 0 to n um b n minus m. So, when we know the z transforms of two sequences un and bn, the z transform of their convolution is equal to product of their z transforms. So, this is the convolution theorem. Now, let us apply this theorem to find the z transforms. So, let us see, suppose we want to find the z transform of z inverse of z over z minus a whole cube, z inverse of z over z minus a whole cube. This is our aim. We have to find the inverse z transform of z over z minus a whole cube. So, let us recall that z inverse of z over z minus a, this is equal to a to the power n provided mod of z is greater than mod of a. So, we know z transform, inverse z transform of z over z minus a is a to the power n. So, by the convolution theorem, z inverse of z over z minus a into z over z minus a. So, this is uz, this is bz, z inverse of uz into bz is convolution of un and bn. So, an star an, convolution of an with an, which is equal to sigma m equal to 0 to n um is a to the power m into bn minus m. So, a to the power n minus m. This is un, this is bm, we have here um, here we have bn minus m, and this is equal to sigma m equal to 0 to n. So, a to the power n. Now, a to the power n is independent of the index m. So, a to the power n can be written outside. This is sigma m equal to 0 to n applied to 1. Okay. So, this is Bun summing, Bun is summed n plus 1 times. So, this is n plus 1 a to the power n. Now, so this is inverse z transform of z over z minus a whole square. We have to again apply the convolution theorem. Now, by the convolution theorem again, z inverse of z over z minus a whole square into z over z minus a. It is convolution of n plus 1 a to the power n and a to the power n. N plus 1 a to the power n is the inverse z transform of z over z minus a whole square, and a to the power n is inverse z transform of z over z minus a. So, this is equal to summation m equal to 0 to n. We can write it as this, we can write as a m, and this we can write as a n minus. We can choose any sequence to write a m. Okay. So, m plus 1 a to the power m and into a n minus m. So, this is um, this is b n minus m. Okay. So, a to the power m, a to the power n m will cancel, and we will have summation m equal to 0 to n m plus 1 a to the power n. A to the power n is independent of m. So, a to the power n can be written outside, then summation m equal to 0 to n m plus 1. Now, replacing m plus 1 by j, I can write it as summation a to the, this I can write as a to the power n summation j equal to 1 to n plus 1 n j. So, this is summation of j when j runs from 1 to n plus 1, and we know the value of this a to the power n. Sigma j equal to 1 to n, j is n into n plus 1 by 2. So, it is n plus 1 into n plus 2 by 2. So that is the inverse Z transform of, so thus Z inverse of Z over Z minus a whole cube, this is equal to a to the power n plus 1 n plus 2 by 2 when mod of Z is greater than mod of a. Now in particular inverse Z transform of Z cube over Z minus 1 whole cube can be obtained by taking a equal to 1 here. So inverse Z transform of Z cube over Z minus 1 whole cube is 1 by 2 n plus 1 into n plus 2 provided mod of Z is greater than 1. Let us take some more examples on convolution theorem. Suppose we want to find inverse Z transform of Z square over Z minus 1 Z minus 3. So let us say let uz be equal to Z over Z minus 1 and bz be equal to Z over Z minus 3. Then we know that inverse Z transform of uz is equal to 1 to the power n provided mod of Z is greater than 1, because we know that Z transform of a to the power n is Z over Z minus a provided mod of Z is greater than mod of a. So taking a equal to 1 here, we get that Z inverse of Z over Z minus 1 is 1 to the power n, and here and similarly Z inverse of bz will be equal to Z inverse of bz will be equal to this is Z over Z minus 3. So we will take a equal to 3 here. So this is 3 to the power n provided mod of Z is greater than 3. Okay. So we know the inverse Z transforms of Z over Z minus 1 and Z over Z minus 3. So inverse Z transform of, hence by the convolution theorem inverse Z transform of uz into bz will be equal to convolution of un with bn. So the required inverse Z transform, that is Z inverse of uz into bz, is their convolution here. So sigma m equal to 0 to n 1 to the power you can write 3 to the power m, this I can write as um 3 to the power m, that I can write as bn minus m. So 1 to the power n minus m, which is summation m equal to 0 to n 3 to the power. Now this is a geometric series and here the first term is 1. So the total number of terms are n plus 1. So we, and the geometric ratio is 3. So we apply the formula, we know that a plus ar and so on, ar to the power n minus 1. This has some a times r to the power n minus 1 divided by r minus 1 when r is greater than 1. Okay. So here we have r as 3. So this is a is equal to 1. So we have 3 to the power n plus 1 minus 1 divided by 3 minus 1. So this is half of 3 to the power n plus 1 minus 1. So that is inverse Z transform of Z square over Z minus 1 Z minus 3 1 by 2 Z3, and the region of convergence here will be the region that is common to both the inverse Z transforms. Inverse Z transform of uz has common the region of convergence as mod of Z greater than 1, here have mod of Z is greater than 3. So the common region is mod of Z greater than 3. So the region should be mod of Z greater than 3. Now let us take up another question. Here we have two sequences. One sequence un is 1 by n factorial, the other sequence bn is also 1 by n factorial, and we are to show that the convolution of un with vn, or you can say un with un, is gives you 2 to the power n by n factorial. So let us say let un be equal to 1 by n factorial. Then we know that by definition of Z transform. Z transform of U1 is equal to sigma n equal to 0 to infinity U1 Z to the power minus n. So, this will give you summation n equal to 0 to infinity U1 is 1 by n factorial. So, 1 by n factorial Z to the power minus n, okay, and this is nothing but e to the power 1 by Z, provided mod of Z is greater than 0. So, the region of convergence here is mod of Z greater than 0, and e to the power 1 by Z, the exponential function e to the power 1 by Z is expanded into the Maclaurin series n equal to 0 to infinity into the Lorentz series n equal to 0 to infinity 1 by n factorial Z to the power minus n. Now, let us find that Z inverse of uz into Vz. So, this is uz. Now, Z inverse of uz into Vz, we know this is equal to un star Bn. So, let us take Bz to be same as uz, okay. So, Z inverse of uz is e to the power 1 by Z, Bz also is e to the power 1 by Z. This is equal to un in star Bn. So, 1 by n factorial star 1 by n factorial, and now we see that Z inverse of e to the power 2 by Z, Z inverse of e to the power 2 by Z. So, it is Z of 2 to the power, this is 2 to the power n by n factorial we have, because since Z inverse Z of 2 to the power n by n factorial, if we take this sequence, this is summation n equal to 0 to infinity 2 to the power n by n factorial Z to the power minus n. So, I can write it as summation n equal to 0 to infinity 1 by n factorial 2 by Z to the power n, and therefore, it is e to the power 2 by Z. So, Z inverse e to the power 2 by Z is nothing but 2 to the power n by n factorial. We have seen here that since e to the power 1 by Z was equal to sigma n equal to 0 to infinity 1 by n factorial Z to the power minus n, from here one can guess that e to the power 2 by Z will be sigma n equal to 0 to infinity 1 by n factorial 2 by Z to the power minus n, and therefore, the sequence that we will get on taking the inverse Z transform of e to the power 1 by Z will be 2 to the power n by n factorial. So, that gives us an idea about the inverse Z transform of e to the power 2 by Z, that we can see from here also the by definition of convolution. So, un star Bn is sigma m equal to 0 to n um which is 1 by m factorial into Bn minus m. So, n minus m factorial. By definition of convolution we can see this, we know that un star Bn, this is summation m equal to 0 to infinity Bn minus m. So, I have just put the values here. Now, I can multiply and divide by n factorial. So, if we do that 1 by n factorial summation m equal to 0 to n cm we can write, multiplying and dividing by n factorial, and this is nothing but the sum of the binomial coefficients nc0 plus nc1 plus nc2 and so on ncn is given by 1 plus 1 to the power n, which is 2 to the power n by n factorial. So, the convolution of 1 by n with 1 by n factorial with 1 by n factorial will give you 2 to the power n by n factorial. From the inverse Z transform, when we apply inverse Z transform here, we know that u to the power n by z is I think I should not have done that. Rather we can see that here yeah, Z inverse un star Vn is 1 by n factorial star 1 by n factorial, and this we do not have to do this, that is Z inverse of uz Vz into Vz, and which is e to the power 2 by z, and Z inverse e to the power 2 by z is nothing but 2 to the power n by n factorial. So, this is 2 to the power n by n factorial we get. So, this is what we have, and with that I would like to conclude my lecture.